Here's how I think of the material in 6.2. It starts with this observation. Every curve has infinitely many equations. So to give you an example, let's start with this curve. X plus 2y equals 1. You know that's a line, so I just drew a line over here. I could make other equations for this same line by just doing a little algebra of this curve. I could multiply both sides by -3, for instance. -3x minus 6y equals -3. To this I could add 4. 4 minus 3x minus 6y equals 1. And you know, that's a different equation than that one. Not much different, but I mean, you could go on forever making more and more equations all for that same line. That's why I say every curve has infinitely many equations. Something kind of special happens though if I subtract x from both sides. That's another equation for the same line. And then divide that by 2, there's another equation for that line. That's kind of special because y is expressed entirely as a function of x. That means that's not just a curve in the plane, it's the graph of a function. But in particular, y is some function of x. That's why this curve passes the vertical line test. But look, this curve is also kind of special because you could solve for x instead of solving for y. If you simply subtract the 2y from both sides, then one of them, among the many equations for this curve, there's one that reads x equals some function of y. So that's not just the graph of a function in the sense that y equals some function of x that passes the vertical line test. It's a curve that also passes the horizontal line test because x is expressible as some function of y along that curve. So I'll remind you what the vertical line test says and tell you, I guess for the first time in this course, the horizontal line test. Vertical line test says no vertical line can intersect the graph of a curve that has the equation y equals f of x more than once. That's because if y depends on x, then along any vertical line, that's where x is held constant, there can't be more than one y. If there were, then y would depend on something other than x on that curve. Well, if x is expressible as a function of y, then the curve must also pass this horizontal line test. The horizontal line test says no horizontal line can intersect the graph of a curve with an equation of the form x equals some function of y more than once. So for instance, when a curve passes of the vertical line test, that means that among its many equations, there's one equation for this curve that reads y equals some function of x. Here I drew one vertical line that doesn't even touch the curve. That's okay. To pass the vertical line test, we just have to know that no vertical line hits it more than once. And when a curve passes the horizontal line test, that means that among the many equations for this curve, there's one that reads x equals some function of y. But when a curve passes both the horizontal and the vertical line test, that means y is a function of x along this curve, and x is some function of y. But we give a name to the x function, the function which equals x, to show that there's a relation between these two functions. They don't describe two completely different curves. Y equals f of x, and f equals, we say, f inverse of y. That doesn't mean reciprocal of f. We'll see in a little while why it's called the f inverse, why it's been given that name. But a function, which, of course, a function whose graph passes the horizontal line test, is called, it's a special type of function. It's a one-to-one function. Every function, the graph of every function passes the vertical line test. Graph of a function means y equals that function of x. But what I'm trying to say is one that also passes the horizontal line test is called a one-to-one function. Well, let me look at an example here. I drew a function here which passes the vertical and horizontal line test. And so it's got, among its many equations, it's got one equation that reads y equals f of x, and another equation that reads x equals f inverse of y. Well, what are the domains and ranges of these two functions? Let's first think about f. Well, the domain of f, those are its inputs. Domain means the set of inputs. And the inputs for f, I can see on this curve, because the inputs for f are x. The x's on this curve go from -2 to +3. And the range of f, I can observe that on this curve too, because the range of f are its outputs. Those are the y values. And the y values on this curve are the interval form the interval from 1 to 5, excluding the 1, because that's an open circle. So the range of f is the interval from 1 to 5, including the 5 but excluding the 1. Well, what about the range of f inverse? Range equals the outputs. And the outputs for f inverse are visible on this curve as the x values, because this curve has the equation x equals the output, f inverse of y. So the x values along this curve from -2 to 3 are also the outputs for f inverse. The inputs for f and the outputs for f inverse are the same. And so this interval from -2 to 3 is also the range of f inverse. What's the domain of f inverse? Well, its inputs, I can see from this equation, are the y values on this curve. So these y values that we've already observed that were the range of f, are also the domain of f inverse. And that in general is true. In general, if f is any one-to-one function, then the domain of f is the same thing as the range of f inverse. And the range of f is the same as the domain of f inverse. So what other things can we observe about one-to-one functions? So here I sort of drew one here to guide me. This one-to-one function here has got an equation that reads x equals some function of y, x equals f inverse of y, and y equals f of x. So the next thing we can observe about one-to-one functions is a little algebra trick. These are both describing the same curve. So I could take these x's here are the same as those x's. If I take this expression for x and put it in there, I'll get y equals f of, instead of x, I'll put f inverse of y. Of course, that's not true for all y. Look, this looks like the range of this function. The y values in this function stop at some number up here. If I tried this for some y value up here, this wouldn't be true. This is true as long as y is one of the y values along this curve. So I'll say that's true if y is in the domain of f inverse, or simultaneously the range of f. They're the same thing. So f of f inverse of y equals y as long as y is in the domain of f inverse or the range of f. And I like to say to myself that I can see why that's true right here. I couldn't express this expression here, f inverse of y, wouldn't make any sense unless y is in the domain of f inverse. Or it couldn't possibly equal y. Look, this is f of something. That couldn't equal y unless y equals f of something, unless y equals unless y is in the range of f. It's one of the outputs for f. So anyway, f of f inverse of y is just y. So I took this expression for x and I put it in there and got this equation. I could do the same thing the other way. I could look at this f of x as being another expression for y and put it right there. So I could take x equals f inverse of y and replace that y with f of x. So x equals f inverse of f of x, and that's not true for all x's. It wouldn't be true for this x out here, for instance, outside of the domain of f. But it's true as long as x is in the domain of f, right? Because look at this in this equation, there it is being plugged into f. This won't make any sense unless x is in the domain of f. And the domain of f is also the range of f inverse, and that kind of makes sense in this equation too, because look, x couldn't possibly equal f inverse of something unless x were in the range of f inverse. The last thing I want to observe in general is how the graphs of f and f inverse are related, because this is the graph of f. The graph of a function is the graph of the equation y equals f of x. Technically speaking, that's not the graph of f inverse, because the graph of f inverse would not be x equals f inverse of y, but y equals f inverse of x. So what would the graph of y equal f inverse of x look like? Well, if I tried to graph y equals f inverse of x, that equation is very similar to this one. The only thing that happened was that the symbols x and y got reversed. It must be that this equation and that one have very similar curves because I obtain one equation from the other by just interchanging the x's and y's. So to get this graph, what I have to think of doing is just interchanging all the x's and y's along the blue curve. So for instance, this looks like, sometimes it helps to draw these things if I sort of make up some imaginary numbers, some imaginary coordinates. So for instance, that might be the coordinate x equals 0, y equals 1. Let's just suppose that was 0, 1. If x equals 0, y equals 1 satisfies that equation, then y equals 0, x equals 1 must satisfy this equation. I just interchanged the x's and y's. So that point on the blue curve means that this point must also be on the green curve. Let's see out here. The x's are negative numbers and the y's, the fact that the blue curve is so close to the x-axis means that the y's are really small positive numbers. So out here the x's are negative and the y's are, I'll say, close to 0. It must be that when I interchange the x's and y's, I'll get points on this curve over here where the y's are negative and the x's are really close to 0. Just as this blue curve hugs the x-axis, the green curve must be hugging the y-axis over here. If I took that point, for instance, this looks kind of like the point, oh, I don't know, x equals 2, y equals 3. Then it must be the point x equals 3, y equals 2 is on that curve, on the green curve. So the thing to observe is that if you want to graph y equals f inverse of x, you could start with the graph of y equals f of x and do something geometric. When you take all the x, y points on one curve and just interchange the x's and y's, that produces a new curve, which is the mirror image of the original curve across this line y equals x. So that's the third observation I wanted to make. The graph of y equals f inverse of x can be obtained by reflecting the graph of y equals f of x across the line y equals x. That's kind of a neat geometric thing to think about. You know, in practice that might not be very useful to us, but it's a good way to think about how the two graphs are related. And I'll just add, you know, reflecting the graph across the line y equals x is really the same thing as just interchanging all the x, y values on the original curve. Let's end with an example of a pretty typical homework problem in this section. So suppose they tell me f of x is 2 minus 3x over 4x plus 1, and they ask me to find f inverse of x. Well, what they want me to do is to rewrite the equation for this guy's graph start off with y equals f of x and rewrite it until x equals some function of y. And when I succeed in doing that, the function of y that I get over here must be f inverse of y. So I want to solve for x in this equation. I'm going to get rid of the fractions by multiplying both sides by 4x plus 1. So 4x plus 1 times y is 2 minus 3x. And now I want to distribute the y's through there. So that would be 4xy plus y is 2 minus 3x. I've got to keep my head on straight because there's two variables here, but I'm trying to solve for x. Not solve for it, get a numerical value for x, but to get x all by itself on one side of the equation with no occurrences of x on the other. So let me subtract this y to get it over here, and I'll add 3x to get it to that side. And the equation will be 4xy plus 3x is 2 minus y. I want to get the x's by themselves. So I've got all the x's on one side. Now let's factor the x out. We've almost got it. I'll solve for x when I divide both sides by 4y plus 3. So 2 minus y over 4y plus 3. So x appears here and nowhere else on this side. We've solved for x. That means this stuff must be f inverse of y. Well now, the problem doesn't ask for f inverse of y, it asks for f inverse of x. But that's no big deal. The name of the function, or rather the function, doesn't really depend on the name of the variable. If that's f inverse of y, I could find f inverse of a by just replacing the y's with a. I could find f inverse of 2 by replacing the y's with 2. Okay, so if they want f inverse of x, I'll just replace the y's with x. Must be 2 minus x in the numerator instead of 2 minus y. The denominator is, 4x plus 3. One other thing they'd like to ask is, what's the domain of f inverse? Well, I've got f inverse right in front of me. It's just a domain problem. There are no radicals. The only thing I have to make sure of is that this denominator is non-zero. So when I set this denominator equal to 0, I learned that that only happens at x equals negative 3/4. So the domain is all real numbers except negative 3/4. So what's the interval of all the numbers strictly less than negative 3/4, union all the numbers that are strictly greater than negative 3/4. But that simultaneously has to be the range of f. That's kind of significant because domain problems are easy. That's a matter of looking at the expression for the function, looking at what restrictions that it places on x, that formula places on x. Finding the range of a function generally is a calculus problem. So it's kind of amazing that we can find the range of this function without doing calculus. What if they wanted the range of f inverse? I don't really think I can look at that and tell you the range, but fortunately the range of f inverse is the same as the domain of f. I think I can figure that up here. The domain of f is everything except the x that causes that denominator to be 0. Only at negative 1/4 does that happen. So the range of f inverse is the same as the domain of f. That's all real numbers except negative 1/4. Finally, I just wanted to say something about why these are called inverse functions. And the answer is right here on this page. It's that when you see y equals f of f inverse of y and x equals f inverse of f of x, that means that the whatever action f does to x, f inverse looks at that output and tells you what the original input was. So f inverse undoes whatever stuff f does. It's like if x is a button you push on the Coke machine and f of x is the can that comes out, f inverse looks at the can and tells you what button you must have pushed. Not every function has to have that property that you can look at the can of soda and tell which button it was. It has to be a one-to-one function. Or, if f was the function that ties your shoes, so f of x is a tied pair of shoes, f inverse would be the function that unties shoes. So if you start with an untied pair of shoes and you tie it, f inverse unties it to return your original untied shoes. And it works the other way around too. If you took a pair of tied shoes and gave it to f inverse, it would untie them. And f would take those shoes and tie them again and return the original shoes you started off with. We saw that in this example in section 6.1. It turns out that these functions are inverses of one another because f of g of x is just x, and g of f of x was also x. That means, for instance, if you're wondering what x would cause g to be equal to 4, well, sticking 4 into f would tell you what that x was. Let me try that in an example. So, in this example, f is this function, x plus 1 over x minus 2. And the inverse function we know to be 1 plus 2x over x minus 1. Let's suppose I wanted to know what x will cause f of x to equal 5. Well, the answer is x equals f inverse of f of x. If you want f of x to be 5, you just calculate f inverse of 5. That's 11/4. Yeah, so I think of inverses as undoing the operation of the function.